This is the next installment for how to wire LEDs 101. We're going to kind of discuss how to wire LEDs in parallel. I'm going to try and keep this as short as possible, but there's can only be so short given the information. So bear with me. Wiring LEDs in parallel, it's very similar to just wiring LEDs singularly. Um, you mostly just tie together the positive side of everything and the negative side of everything. Um, there's a couple different ways that you can go about it. The one that we recommend the most is to have a resistor per LED. We also get a lot of people that ask us about using a single resistor for a bunch of LEDs in parallel. This isn't as ideal, but it is possible to do this. Just to go over some of the reasons why you might want to wire LEDs in parallel as compared to series is it can simplify your circuit in a certain regard. And we find that this is usually the most common reason. Another reason is if you don't have enough voltage in order to wire things in series. As you wire more LEDs in parallel, your voltage requirement doesn't increase. And if you wire them in series, your voltage requirement does increase. The other reason that we usually find is it can be quicker to wire them in parallel in specific scenarios. It can also be quicker to wire them in series in certain scenarios too, so it really just kind of depends on your situation. So one of the things to remember when you're wiring in parallel is when you add more LEDs into your parallel array, the voltage requirement does stay the same, but the amount of current that you need increases with each LED. For example, if you have 5 LEDs and individually each LED requires 20 milliamps or consumes 20 milliamps, then your parallel array will draw 100 milliamps approximately. The other thing that you need to remember that if you are using a single resistor for an entire parallel array, then it is essential that you don't mix the LEDs with any other colors or any other lights of or colors of that particular LED. They should all be the exact same LED. Even having, let's say, 2 green LEDs from 2 different manufacturers can kind of throw a wrench in how the power is distributed across the whole array. So the first scenario that we're going to go through here is wiring 5 green LEDs in parallel with a 5-volt power supply. And we're going to use an LED per resistor in this scenario. And you'll see this is almost identical to just wiring a single LED, with one aspect of tying all of these single LED setups together. That's all this really is, the first scenario. So here's the 5-volt power supply that we're going to use. And we're also going to use these particular green LEDs as well, and the specifications on them are 20 milliamps at approximately 3 volts, 3.0 volts. So here's the power supply. It's just a 5 volts, 1000 milliamp, 1 amp power supply. Now at 75% of its capacity, you could run approximately 37 LEDs off of this power supply. You can run a little bit more, And you can also just run one LED as well. It doesn't matter because it's a constant voltage power supply. This is the particular LED that we're going to use. We're using the frosted lens version of the green 5mm round top LED just because of the lens visibility in the demonstration later when we wire them all up and show you. If you scroll down here, the additional information tab, you'll see forward voltage here is 3.0 to 3.4 at 20 milliamps. I typically recommend going with the lower voltage, so you could base your calculations off a 3.0 or 3.1, and it may actually draw 18 milliamps or so at this particular voltage, but it will be very close. So that's the pertinent information that you need there, forward voltage and the current. So we'll go back to the guide here. We chose that particular 1000 milliamp power supply because it's a small power supply relatively, and we only need 100 milliamps, so we're underneath the threshold of what that power supply can supply, so it's a good fit for the project. So let's go on to calculating the resistors and choosing the appropriate ones. If you watched our previous series on single LED wiring, this will all look very familiar, so I'm going to try to run through it a little bit faster, especially since I will run through it again in our second scenario. So these are the two formulas. Voltage is equal to current times resistance, and power is equal to current times voltage. And these here's what those are measured in: watts, milliamps, amps, and ohms for resistance. So the first thing we're going to do is calculate the resistance value for each LED in this array, which we can treat them all individually. So we have 5 volts, which is our supply, and the LEDs consume 3 volts, so we have 2 volts that will need to be dropped across the resistor, and there will be a current of 20 milliamps or 0.02 amps that will run through that resistor. So we will get a 100 ohm resistor when you calculate that out. This is one of the more important values. You typically will see quarter watt or higher resistors out there. But anyways, the 100 ohms, it is very important. You don't want to go underneath that value. I apologize, the screen jumped around there. So the next thing that we need to do is calculate the power rating for the resistor. This is also very important as well, but it will have a less effect on your LEDs as long as you go over the power rating. And the power rating is how much power that the resistor can dissipate, which is how it gets rid of the excess power. And the formula is power is equal to current times voltage. So we go ahead and put in our values: 0.02 amps times 2 volts, and we're going to get 0.04 watts, which is very, very small amount of power. A quarter watt resistor is 0.25 watts, so we're well underneath the rating for a quarter watt resistor. And this value won't hurt you if you go over on the resistor rating. It won't make your lights any dimmer or anything like that. So quarter watt resistor is perfect for this scenario. So we'll go ahead and choose the actual resistor. So if we look at the resistor values for quarter watt resistors, we will go ahead and see what the closest one is to 100 without going under. And there's actually a 100 ohm quarter watt resistor. So since there's an exact value, we can go ahead and use that for our chosen resistor. So here's what the array is going to look like wired up. We'll do an actual in-person wiring as well, but this is just a wiring diagram. So we have our LED here. This is the positive side on the left here. And so the current comes into the LED, and the resistor in this diagram is actually on the negative side, which is completely acceptable. You could actually put the resistor on the positive side as well. It's not going to make much of a difference for you. But you can see each LED has its own resistor, and this is the universal symbol for resistors, and this is the universal symbol for LEDs or diodes over here. So you can see all of the LED positives are tied together, and then separately all the negatives are tied together, and then they just connect in one spot to the ground. And on the positive side, it just connects into one spot for the power supply there, plus 5 volts. So this is our preferred way to wire LEDs in parallel, and it's going to be the most reliable, and it's going to return the best results. Not that the second scenario will necessarily return bad results or be unreliable. It's just this way is the best way to go about it if you have the option and the time to do so. The second scenario requires using just one resistor for this whole array. We're going to build the exact same array, except we're just going to use one resistor on all 5 LEDs. One of the reasons that you might want to do that is, 1, it can be faster to do that. 2, you may not have the space to add a resistor for each LED. So those are a couple options. I wouldn't let cost deter you from using a resistor for each LED, as resistors are very cheap. So we're going to use the same green LEDs and the same exact power supply. The biggest difference here in our calculations, we're going to use all the exact same formulas, but we have to treat all 5 LEDs as if they were a single LED for the calculations. So we'll have to do some preliminary calculations before we can input any values into the formulas. So here's the same formulas. Voltage equals current times resistance, and power is equal to current times voltage. Alright, so first off, we're going to calculate the resistance value. We rearrange the formula as we always do. R is equal to V over I. So we're going to base our current off of the whole structure. So remember, in parallel, the voltage requirement doesn't increase for each LED that you add in parallel, but the current consumption does. Now we have 5 LEDs, and each of them draws 20 milliamps approximately. So if we look at this as our preliminary calculation, 5 times 20 milliamps equal to 100 milliamps. So essentially we have a 3.0 volt LED that draws 100 milliamps, since we're treating all 5 now as a single LED. So I'll go ahead and input that in. Really the biggest thing that changes here is the current. That's about it. So we still have the 5 volt power supply minus the 3 volts of the LED, and we will divide that by 0.1 amps. So our new resistance value is 20 ohms. Now you can see it's a big difference. For the single LED, it was 5 times that value at 100 ohms. So that would make a pretty big difference in the performance of your LEDs if you used a 100 ohm resistor here. But we will continue on. So we will calculate the power rating for the resistor now. And this is essentially the same as before. Again, the only thing that changes is our newly calculated current for the whole array. Now that's very important, and you'll see how much of a difference that makes as well. And it's also good to note that the larger difference in the power supply voltage compared to the LED requirements, the larger of a power rating for your resistor that you will need. So in this scenario, the 5-volt power supply is great because it's pretty close to the requirements of the LED. It's only 2 volts more. We would see a much bigger value for the power rating if, for example, we use a 12-volt power supply. But that will be something we'll touch in probably on the next series. So, anyways, let's go ahead and calculate this out. Power is equal to 0.1 amps times by 2 volts, and we're going to get 0.2 watts. Now, for just a single LED, it was 0.04 watts. So you can see it's substantially more dissipation for this single resistor in this scenario. Overall, if you were to add up the power rating for all of the resistors in scenario 1, it would equal 0.2 watts. So this isn't more efficient necessarily to do it this way, other than the fact that you're using just one resistor instead of 5. So, but this does change, in my opinion, the resistor that we should use. So even though 0.2 watts is less than 0.25 for a quarter watt resistor, it's pretty close. So there's no reason to not bump up the resistor power rating to a half watt resistor. So let's go ahead and take a look at our half watt resistor page and see what the closest value is to 20 ohms without going over. If you're looking ahead here, it's a 22 ohm half watt resistor, but we'll go ahead and just take a look. So we'll go head on over here. These are the half watt resistors right here. So 22 ohm half watt resistor is going to be your best value to choose. You wouldn't want to choose the 18 necessarily because it's less than the resistance value that we calculated. So the 22 ohm would be perfect. And I don't usually recommend running the LEDs at 100% capacity anyways. So that works out perfect. It'll just ensure the longevity of your circuits and the LEDs most importantly. So here's how this configuration is set up if we looked at a wiring diagram for it. And you can see how different it is. We have our 5-volt power supply coming in, goes into the resistor, and then across this array here, you will have a distribution of that 100 milliamps evenly across all of these components. And that is why it's super essential that you use the exact same LEDs if you're going to wire them like this. To ensure the longevity of it, to ensure the quality of your end product as well, because if there's anything different in these, then the power will not get distributed evenly across them. So you can see all the positives here tied together just like they were before, the resistors before the positive. That is the one thing that changed. It doesn't matter. We could have put it on the other side as well, but this works just fine. So you can see how this may be a little bit simpler, and in certain situations it may be the best way to go. So that's everything on how to wire LEDs in parallel. In the next series we'll kind of look at tying everything together. Parallel and series single LEDs, they kind of all go hand in hand. So we can make combinations of circuits in order to optimally wire LEDs in pretty much most all scenarios. Here's the assembly that we made in scenario 1 with a resistor for each LED. We have the power supply set at 5 volts and the power on the common rail over there and the ground on the common rail over by the resistors. It also doesn't matter where you connect the positive and the negative in this setup as shown. It'll work just fine either way. The other thing to note here as well is we set up the resistors to be on the negative side of the LED, just like the diagram in the tutorial. You could have just as easily put them on the positive side of the LEDs too, and it won't make much of a difference at all. Here's the array that we created in scenario 2, where we have 5 of the same green LEDs using just one resistor. We have the power supply set at 5 volts. We have the positive coming in before the resistor, and the negative, apologize for my hand getting in the way, can be connected anywhere on that common rail for the negative side of the LEDs. And I've moved it around here in a few different locations just to kind of show you that it's okay and it'll work just fine wherever you connect it on that common rail. Felt the resistor there, and it's lukewarm at best, so the half watt resistor was a good choice.